Okay, hello everyone. We are talking about multi-computation and it's broken into several topics. The representation of the process of evaluation, the making of evaluation be not just single path, but multi-way. And I guess we start off, we also had talked about situationally aware function application. So where should we start? Should we start talking about evaluation graphs? This is the new stuff from Ian. Is that correct here? And we also have new stuff from Nick on evaluation graphs. Is that a true statement? Ian?
Yeah, yes. So that's a mock-up of representing trace as a graph using the two kinds of edges that we discussed.
Okay, so to understand this picture, okay, this is evaluation of f of 3, the Fibonacci, and this dotted line, horizontal dotted line, represents a transformation rule. Is that correct?
Yep.
And the solid line in the vertical direction represents a recursion into the expression.
Yep.
And what does this dotted line here represents basically just the fact that that thing survived from there to there to be used in here. Is that correct?
Yeah, you're matching the result of evaluation into the next step.
And is there a well-defined, I mean, why would we not just go from that token effectively directly into, no, I'm confused by this.
Well, so this way, every expression ends up getting represented as a tree. So the point is, this is kind of a graph where the nodes are entire trees.
Okay, so people who know about the whole multi-way world, which is not as many people. Okay, this is like a global multi-way system. Is that a true statement? Or this is a single-way version of a what if we went? I'm confused here.
So essentially, there's an edge from f of 3 minus 1 plus f of 3 minus 2 to f of 2.
Okay, so here, this wants to get to here.
Mm-hmm. And the way I'm representing that is just by connecting all of the leaves.
I'm confused here. So this f of 3 minus 1 ultimately is going to turn into f of 2.
Yes.
But the things turning into things edges are two kinds. The horizontal are ones where a transformation was made. The pseudo-vertical are ones where...
So they will always connect identical nodes.
Okay.
Like, so you have an F from an F and a 2 to a 2.
Okay. Okay. Nick, is this relevant directly to what we're talking about right here? Or is this something different?
It should be relevant. It's another representation of how multi-evaluation can work. Not the trace as it is right now, but all the possible paths, how you can evaluate it.
Oh, I see. So this is the multi case, because this case here is still the single way case.
Right.
This case here is drilling inside the evaluation for a single way computation. And
right, and I think the left is the actual trace of the standard evaluation sequence, and the one on the right is the more fundamental operation of just applying rules.
Okay, so the claim is this is a representation of the evaluator, and the representation is if you see f of 2, this here could be a labeled edge that corresponds to an event that is the apply the definition of f event. I mean, in other words, this edge could be labeled with a transformation, right? F of n blank colon equals whatever.
Yep.
Correct? And it might be useful to do that because in a bigger version of this picture, that transformation rule will be sort of floating out there in the ether, pulled in to that edge to produce this result. Am I making sense?
Yep.
But that edge is labeled that way. Now, this edge, can somebody unravel this? Nick, James, somebody else? Is this like a causal edge in our world? What the heck is that edge that goes from F to F? Do we have any analog of that?
No idea.
I mean, we would usually just have what, Nick, like a loop in the graphs that we've seen before.
Well, yeah, if it's like the same F with the same semantics, then yeah. But here it's like something happened to it. It might be being observed or something.
Well, okay, what happened to it is that it is being put in a new expression.
Yeah, in my mind, it's a position spec encoding.
No, but this it being inserted in a new expression, this is like in the combinator case, these weird repositioning links in let's take a look here. There is this idea of a kind of in the DAG. Let's see where I have this. A lot of irrelevant stuff here. Let's see. Oh, there we go. This might be it. Okay, this is a rewrite in which the F has been shared there. And when the F has been shared, after, I don't know if I discussed that here. I discussed that somewhere. After the shared, that's right, the shared F has to be, something might happen to it, but it has to be reinserted back into the expressions it came from. If that makes any sense.
So Nick, can we treat the F as a token? So we have these, can we treat these as two different states and the F as a token that belongs to both of them, Nick?
Oh, I see. That's
with this
Yeah,
framework that you have.
Yeah, it's very close. Yeah, it's also related to the
so this
global
is-
multi-choice systems.
Yeah, right. So this is where Nick's, choice to include states into tags can come in handy. Right.
okay. So, but basically, what you're basically going to say is that this F of 3 minus 1 is going to be a state, and the F is going to be a token.
That's right.
Yeah.
Mhm.
And then what this is saying is that certain tokens, boy, what's weird is this tree-like separation where a token can have subtokens. And the thing is that the transformations can happen at any level in this expression tree. Like the 3 minus 1 could be transformed.
Well, here it is like
Say if you had
there's
a function with, oh, sorry.
Go on.
well, here it is like an implicit state is also created here. You can say that your initial expression is being mutated at that particular position. So every time you look at the sub-expression and decompose it into tokens, it's like you're making up a new original expression. So it's like a new state altogether. So it's not like you just drilling down into one token and decomposing it. It's still it's like you're decomposing the initial expression again.
Okay.
So you're suggesting that there really aren't sub tokens, so to speak. Any sub token that you can imagine is just another different position, just a different sub expression, different sub tree that belongs to that state. Is that the idea?
Well, the thing is, you can't modify. If you modify the 3 here, or if you modify the 3 minus 1, you are implicitly modifying f of 3 minus 1.
Well, so can I make a point about functions with like a hold attribute? They
Yeah.
wouldn't have those tree edges downward because you only have the tree edges precisely when you're doing the standard evaluation sequence. So if
Right.
you had a function with a hold attribute, then you would just have a node with a horizontal line to another node,
I understand.
right? And so they genuinely are new expressions because what you're doing is you're evaluating the sub-expressions. So the fact that there's an f to an f, that's just because f evaluates to f.
I understand.
You
but
know,
you're
if
going
f
to
had an own value, that'd be like f goes to something else.
Look, the weird part about this is this whole thing, this f of 3 minus 1, evaluates to f of 2. It does that by subparts of it evaluating.
Mhm.
But then you have to reconstruct from the subparts. You have to, what you've got is essentially some kind of weird parallel transporty thing where there's this representation of the expression, which is f of 3 minus 1, which is subdivided like this, right? Because this is a very different, okay.
Because
There is-
f doesn't hold its arguments. But
Yeah,
yes.
assuming it doesn't hold its arguments. There's a notion of subdivision edges and there's a notion of equivalence edges. See, this f of 3 minus 1 being joined to 3 minus 1, that isn't the same kind of thing as 3 minus 1 being joined to 2, because
Right.
that edge is fundamentally an equivalence statement of some kind. Or,
The
you know,
transformation.
this is equivalent under transformation to this. Whereas this is known to be drilled down.
Yeah, this is saying I need to evaluate 3 minus 1 in order to evaluate f of 3 minus 1.
Which somehow relates to causal graphs. In other words, in order to do the evaluation of f of 3 minus 1, that is sort of the definition of a causal graph, is it's giving you the causal dependence, the event you are about to do, what events have to have already happened to be able to do that event. And here, what we're saying is, to evaluate f of 3 minus 1, we have to already know what happened to 3 minus 1, et cetera, et cetera, et cetera. I mean, it almost feels like this should be a dependency the other way up. Like seems like it's going down and saying f of 3 minus 1 turns it into 3 minus 1, but it doesn't. It's 3 minus 1 contributes to f of 3 minus 1. Did that make any
If
sense?
you start with f of 3 minus 1, and then you transform it by transforming its parts.
Yes, but what I'm saying is that those parts
I
are
think
dependencies.
I think there's like are you doing the replacement in place, or are you constructing a new expression kind of thing?
No, I'm really not saying that. Let's take a look. Okay, I think I understand. Do people understand this picture, basically? And how much by hand was this done? Is this like literally done by hand, or is
The
there...
embedding is by hand. There is code in there in the cell above.
Okay,
it.
are these ones that are automatic, or...
So the top one is what you would automatically get. Just the g equals trace graph of f of 3 gives that.
My gosh. And who can understand this?
You really need the embedding. The point of the embedding is that the horizontal axis always represents transformation rules, and the vertical axis always represents like sub-expression recursion.
Except it
And that's
doesn't.
violated.
The vertical
that's
axis
violated in the automatic embedding. So
I understand, but the vertical axis, the vertical direction, also is this stay the same, thing.
Well, it's only there because you did sub-expression recursion. You had to evaluate plus.
Yeah, but the evaluation is not horizontal. You're telling me evaluation is horizontal, but it isn't, because this evaluation, which did nothing, is vertical.
I'm saying anytime you have an evaluation, you are going to, at the very end of it, have a vertical edge connecting the result of that evaluation to the sub-expression in the new expression. So you're right that plus doesn't have a horizontal because no transformation rules were applied.
So you're saying...
I'm saying the top plus
case
is the input, and it evaluates to plus.
Okay, but I'm pulling this back to saying we're going to fixed points. And what you're now saying is once you reach a fixed point, there are really three things that can happen. Okay, a transformation, a drill down, and a fixed point that is just transported to the future.
Right. So the first two, you either do a transformation or a drill down. Those are the two operations. You do those continuously until you reach a fixed point. Either one, any mixture of them, any mixture of functions with different attributes.
Yeah, okay, I get it.
So they're together. And then no matter how you got the result of the evaluation, at the very end, when you reach the fixed point, you have a vertical edge connecting that fixed point into its corresponding part in the next step.
And why does that 2 not have an outgoing edge?
Well, because you did trace original goes to, this is trace original goes to, oh no, it's because the 2 is already evaluated. 2 was the result of 3 minus 1.
Okay, but why doesn't it survive?
It doesn't need to, it does not need to reevaluate because it's the result of something that's already evaluated and no transformation rules have been applied.
I see. So this is in fact the reevaluation attempt. A vertical line is a failed reevaluation attempt.
Well, a vertical line is an evaluation attempt. Oh, so you mean a strictly vertical?
Yes.
It's only strictly vertical if it happens to be the furthest one to the left.
I see.
I'm just saying you always, anytime you've evaluated an expression, are going to end up somewhere with a vertical edge from the result to the next step.
I think I understand. All right, let's take a look at Nick's thing over here. Is this
Well, I guess
now...
would it be possible to just omit the last that last reevaluation edge, or does it not work if you do that?
You're talking about the 3 to 3 at the very end?
Yeah, like I mean, if you're always going to get, if it's always going to be the case that the last step when reevaluating it doesn't change anything, maybe you could omit that edge.
Problem is, how does this plus get itself reinserted down here? That's what I'm.
So, for example, look at the 3 minus 1 horizontally goes to 2, and then from there vertically goes to a 2.
Right, 3 minus 1.
The lower 3 minus 1. So
that how did it go? Wait. How did the 3 minus 1 go from there to there?
Well, so 3 minus 1 doesn't have any special transformation rules. You you evaluate its arguments. So plus evaluates the plus, 3 evaluates the 3, minus 1 evaluates the minus 1. You get 3 minus 1 again. You apply a transformation rule, you get 2.
Okay, but this 3 minus 1 here came from
there's no edge from the top 3 minus 1 to the bottom 3 minus 1.
Well, what is that little thing above the 3?
That's the edge from the 3 to the 3.
Going down there.
Oh, that's confusing. It looks like there's an edge.
Yeah, because they're overlapping.
Okay, but
so is it the case that for every kind of inert object, like a 2 or like a plus, that there'll be a vertical edge from it to itself?
With trace original goes to true, yes.
Okay. But would it be, I mean,
trace original goes to false is explicitly the thing that hides that. If you have an expression that just evaluates to itself, it doesn't show up.
Oh, I see. Does that make it like disconnected or something weird like that? Or does it just work? It's just a bit less hairy.
Well, so we were looking at the trace original goes to false above, and basically you just end up with fewer duplicates.
Okay,
but I'm still very confused about this 3 minus 1 giving a 3 minus 1.
It breaks apart into its constituent parts, which evaluate.
Yeah.
Then you look at the thing that you've gotten, which is 3 minus 1. It's just the tree.
Okay, but how did it get from that 3 minus 1 to this 3 minus 1 here?
That's what I'm saying. There is no edge from the 3 minus 1 to the 3 minus 1.
That's why I'm talking about parallel transport, that it somehow...
Yes, plus goes to the plus, the 3 goes to the 3, the minus 1 goes to the minus 1. And if you make a tree out of those 3 things, that's 3 minus
back
1.
what you had before, as it turns out in this case. But only then...
I'm just labeling that node with...
This is super confusing. It's only then, after the evaluation...
Apply construct. Like you construct...
I understand, but after reconstruction, then it goes in to evaluate the main head.
Mm-hmm.
I think this is confusing. I think there's got
Does
to be,
plus doesn't hold its arguments.
yeah, right. But I think there's got to be a better way to do this. That doesn't have the weird redundancy of this thing.
Pull back up. That's just trace original goes to false.
Okay, but this thing, just to complain again, this thing goes down to evaluate its arguments, flows back up to here, then flows back down to here.
No, I'm saying it goes down to the plus, down to the 3, down to the -1. Those things flow down to the plus, the 3, and the -1.
Oh, I see. And then those flow back up again here to the 3 - 1.
Yeah, using construct basically.
Okay. Well, I'm going to be interested to see Nick's token event graph version of this. Okay, and this is
that's the version where you don't see the redundancy. You see the 3 - 1, you don't see another 3 - 1 with everything just being trivially connected to a copy of itself.
Is there any value to having the trivial connection to the copy of itself? Not obviously. Okay.
Yeah, I mean, it's easier to implement, and we have that option already, so I don't know.
Okay. All right. Fine. So let's see. So Nick, should we talk about this now, or should we go to your token event graph thing?
No, we can briefly talk about this one.
Okay. All right. So
Like, this is simply like manually construct the rules. It's like you insert your down values and see what happens. You just have to hack around something about how you evaluate plus.
okay, but the basic point here is that by the way, I'm just looking at where these things are getting saved. Did that get saved in the appropriate place?
I have this notebook in our multi-computational folder already.
Okay. Wait a minute. Multi-computation supplied trace was already there.
You can replace it. I put it in there before the meeting started.
Okay, fine. But I don't want to replace it. I might as well just
Okay.
use that one.
Okay.
Okay. Okay, so let's go here just for a second. Okay, so if I were to take this code here, so I understand, this is a multi-replace on expert using the Fibonacci rules.
Yep.
So let me try to understand this. So there's an event that turns it into that. That is using the Fibonacci rule as an event. This is another event. Now, I don't understand why it's turning in, why that event has two outcomes there.
Because it's still one event, because here event is a simple application of multi-replace, and multi-replace produces multiple results.
But so
depending on what happened.
So the event here either expands f of 3 or it expands f of 2. Is that correct?
Yeah.
Transforms one or the other of those.
Or is it that it does both?
No, it does. It does one going this way and one going that way.
Mm-hmm.
And so this is a confluent system, which, regardless of what order these things are done in, always leads you to 3.
That's right.
I just want to see the thing just for fun. I want to see a okay. So just for my understanding, this is interesting. I mean, this is basically, okay, so this is multi-way Fibonacci recursion. And any particular, so leftmost, outermost. So we should be able to label this with, leftmost, outermost goes down one side. Is that right? Actually, we didn't even get to the end here. Let me just go to the end. Oh my gosh, we didn't get, now that should have gotten to the, I mean, by this point, Okay, so there are two kinds of events here. One is an addition event, and the other is well, maybe three kinds. An addition, an F transformation.
No, it's just one kind. It's just multi-replace contains all kind of rules. Maybe it's like I could make different events by just like applying different rules.
I see. Okay,
Yes.
but I mean, so your multi-replace here has it's greater than 2 in active plus. Otherwise, this blah blah blah. What the heck is that rule there?
Basically, evaluate plus.
Oh, I see. That's saying that that's saying that inactive plus is going to turn into active plus. Well, that's interesting.
But only for integers, right? It's not a complete. It's not an exact way how evaluation of this thing works, but somehow you can expand more, like how you activate plus on something else and so on.
Okay, so that, for example, it doesn't do the simplification here of saying that there are two F of 2s here, which can be combined.
Yeah.
So just so I understand, the path that corresponds to the usual recursion, the usual evaluator, is a particular path here. Can we easily find that path? Maybe we should try a simpler case. Where is the evaluator path? F of 3 plus F of 2. And then the next step for the evaluator is actually none of these paths. It's a combination, isn't it?
No, it always evaluates one sub-expression at a time.
I know. Whereas the evaluator actually effectively evaluates multiple sub-expressions. Doesn't it?
Why?
I mean, what would this look like? What would the path that
I
corresponds
think
to
it's
what
just the
evaluator-
leftmost path, I think, is the sequence that you would get from the evaluator. So there you would end up evaluating
Oh,
F of
I
2
think you're right.
first.
I think you're right. Okay, let's see if it's still the leftmost path here. You might be right. Okay. Now, in this case, all evaluation paths are the same length, for example. Right. And okay, so that's, but now, although they aren't necessarily the same work because they could be different sizes of expression on the way down and so on. Okay, I think I understand this. So that's a single multi-replace. And the single multi-replace here has like two outputs. One, it evaluated the 3 by using the inactive plus goes to plus rule, and the other it evaluated F of 3 by doing this.
Yep.
Okay. Okay, so this is essentially how. So is it the case that you could make a picture like this for any evaluation of making the evaluation multi-way? By simply using
so.
multi-replace. Go ahead.
I think so if you do some preprocessing on the rules or the down values somehow.
But so basically every expression would naturally turn into an active version of it, but then you'll have to have rules like this that progressively recurse and evaluate.
Yeah.
Right.
I mean, so you would basically have to write the evaluator as a list of replacement rules.
Well, right. And Nick doesn't yet have the problem here of any kind of drill down in the evaluator. This evaluator is its only evaluation step is to replace, inactive plus with plus at the top level, so to speak. It didn't have to do drill down and then replacement.
Well, it's not the top level. It's like,
What do you get if you if you get rid of the blank integer on the X.
Let's try it.
Like, will the right answer still be in there somewhere, but it just takes more paths? Triple.
I'm not sure I want triple. I think triple might blow up.
Okay.
My gosh, what the heck is this doing?
I think now you have like an effect of activating plus. It also commutes your arguments.
Okay, so that's causing some equivalences that weren't there before. Is that what you're saying?
Yeah, and then this plus, because the rule expects an active plus on the left hand side. It's not getting replaced anymore.
What's not getting replaced anymore? Oh, I see.
Well,
The plus after you've done one plus, it no longer knows to replace that plus because it is now a raw evaluatable plus, not an inactive plus.
Yeah.
Okay. All right. Were you going to show some token event technology, or is this it? Nick?
No, the
there's
only
more.
technology that you can add an additional option to the token event graph. You can even try it for this one. It's called state vertices. Goes to true, and there's like an additional type of vertex is going to be added that indicates states. And now it's like no longer a bipartite graph, but it's like a tripartite graph or whatever.
Okay, what the heck is going on here? So those bluish vertices, blue-green vertices, those are state vertices.
Yep.
Right.
And
the idea that you have some kind of operation of how would you decompose your states into tokens and how you recombine tokens back into states. By default, the recombinations is just an identity. So your state is just a list of tokens. So in this case, it's just a list of expressions or set.
why is this a state? I don't understand why this is a state, because these all seem like completely different expressions.
Yeah, they just being combined into a state, which would be just a set of tokens. By default, this is the state. But you can, by defining your own recombination and decomposition functions, you can make different kind of states. For example, if your token would be labeled by position, you can write a function that can make a tree out of tokens or an arbitrary expression. So your state would be an expression again.
I'm fairly confused. I mean, why do the events? Okay, so we made this state here. This state is a multi-way combination. I mean, so in this direction, it's the branchial direction. This is not the tree direction. This is a branchial direction going from here to here. These are different branches in the multi-way graph, correct? Getting to these different tokens. Is that a true statement?
Yeah.
Okay, so then all these branches are combined into a state which has branchial extent. That state has branchial extent. It's not there's some states that you might say have some kind of tree-like or spatial extent, like they're a list and they have multiple things that are almost like different places in space, or some kind of expression that is
but Nick, the state should have some, in many cases, the state should have some tree-like extent, with the tokens basically being subtrees.
It depends how you make a state. It can be not even be unique. It's like every time you recombine tokens into states, it can be more than one state. It's like in this case, the default behavior is just make one state out of all the tokens at each step of your evaluation.
Do you have a simpler
Yeah,
example?
yeah, right.
What's another example? Did you have a file of examples, Nick?
I have one example where it's like have multiple states.
Okay. Where is that?
Well, in the multicomputation folder, there is a token state event graphs.
Okay, what the heck is this? Okay, that's an ordinary nm goes to n times n minus m. Okay. Token recombination function. All right, what the heck is this?
Hold on. Have some Zoom problems. Sorry,
Okay.
I lost my window.
Okay, does anybody else understand what's going on here? Well, while Nick is recovering his. So there's a times and there's a minus on that edge. I see. That event generates a times piece and a minus piece. Those
Yeah,
generate
okay.
two different tokens, and they're labeled which one is generating which token. So this is essentially a graph with ports, where
Nick,
you're
are
specifying.
Are you back? Nick?
Yeah, I'm back. This is just a feature that you can tag every output or even every input if you have an association. But the point here is that you have multiple states by giving some kind of recombination function that makes multiple outputs as states. So
Okay,
here,
but you've already got
I
a different thing, which is quite interesting, which is the ability to have a graph whose outputs are edges that are tagged like this. We don't have that in an ordinary graph, right? If I say graph of, A goes to, let's say, X goes to B, Y goes to A, I don't believe that does anything useful. I don't know what that's doing.
oh, this is going to make a vertex which is an association.
Boring. Yeah, okay. But so that's the type of syntax that we would need for a graph with ports, isn't that right?
Could you also do a undirected edge and an association?
Yeah. So how does that help anything? I mean,
Then what if you have an association on both? And what if you want a vertex that is an explicit association?
yeah, well, that's an issue. Okay. No, I mean, all right, fine. So it probably needs a wrapper. To be something that, a ported wrapper or something, or a ports wrapper. Am I making any sense? I think there's nobody from the graph theory group here. But I'm just trying to.
How is it different by just adding a tag to the edge? How we want it?
It may not be different. Can I add the tag? In order to add the tag, I have to explicitly say graph of ABC, for example, and then I've got the edges tagged. What is it called? Oh no, edge.
It's just a directed edge, and you can add a third argument.
Right.
Are ports? I'm not familiar with graphs with ports, but are the ports?
We don't have them yet.
No, I mean just the idea of them. But would they be
Ports are
ordered
just
things?
labeling. What's that?
Are they ordered things like this port comes
Yes.
before this one?
Oh, I
So
don't know. Actually.
Tags don't accomplish that.
The hell? You're saying ordered, I see. You're saying ordered as in tag 1 comes before tag 2 in the description of tags. Yeah, it does
And
not.
even without an association, just ordering for the, I guess that's mostly useful in a DAG or a tree where you might want ordered siblings.
Right. I mean, the limiting case of this is a tree. The limiting case of a graph with ordered ports is presumably a tree.
Well, tree's more restricted than that.
No, I understand that, but a tree is an example of a tree could be made by making a graph with ordered ports. True statement?
Yep.
Okay. So, Nick, what should we understand here from this picture?
Now, I think the main point here is that you also have additional multi-computation. I don't know how do you call it? The fact that the states can be multiple states, multiple ways of how you produce states out of tokens.
I'm still confused by this.
It's an additional multi-computation.
So where,
aspect.
Nick, where's the example where you're producing different states from the tokens? Because it seems
So
like
here is an example. It's you have two states at each time at each evaluation step, your tokens produce two states.
but they're distinct tokens. It's not like the tokens are going to different states. It's just you have the 4 and the 0 are going to this left state, and the 1 is going to the state on the right. Right.
Yeah.
What happens at this? Can we evaluate it at an additional step? Does it get more lively?
Then you have an additional step. You have like separate events that act on different states.
I just wanted to see what happens next.
This is not
Here's
easy.
like,
I mean, so Nick, when you were describing before that, your state, you can treat your state as an expression. Tokens can be, sub-expressions. They can provide basically position data about the state. That was intuitive. Is there some example we can take that's more familiar, where we take some tag that we used, say in MetaMath or somewhere else that's quite familiar, and we just add these states? Maybe an example where the states will be some clear expression with some tree-like structures.
I don't have it yet. Like a nice functionality when you have a tagged position tagged tokens, and then I recombine them into expressions.
What do these numbers mean? The 2, 1, etc. What are those?
Those are just the indices of the tokens in this case, I guess.
So, okay, so this is saying, so in other words, this statement that 4 is at the 2 index and 0 is at the 1 index means that in terms of Wolfram language representation, that state there is 0, 4, the list 0, 4. Am I right?
Right.
Can we show that? Can we put labels on the states here?
I think I'm not storing the state and this like representation the state vertex at all, but the event kind of shows them. If you show the labels for events, they show the position where those events being applied.
But what happened here? We've got lots of competitors for the 2 slot. What's going on? What are we
I'm
supposed?
not sure. I'm not sure how I'm labeling the in state. I'm not sure how I'm tagging those edges. It's just some arbitrary tag, maybe.
Okay. All right. Okay. Fine. Okay.
So wait, Nick, at the moment, is it not possible to take a token event graph that we've used before and activate this new option that you've included?
What option?
Well,
The
this
state
state vertices option. That's what I was asking before. I mean, token event graph, we've used token event graph plenty of times. Can't we just take a more familiar example of a tag and
Well, if you
include
just
this option?
turn it off, well, we can, I guess.
Fair enough. No, but what James is asking is, things we've studied are like the n plus n, n minus n. But this is fine. This is one like that. What is token recombination function doing?
Just specifying how you make those states out of tokens. Here it just makes two states. One combines odd numbers and another even numbers.
Okay. What is there
The
a default? Yeah.
Default one is just union, basically. So it's always going to be one state at each step.
Oh, I see. Okay. Oh boy.
I see. Okay, so this is essentially a distributing tokens to states function. It's saying of the states that are there, how should these tokens be arranged between the states? Is that right?
Yeah. So if you're going to think about expressions, then it's going to be more interesting. How you recombine sub-expressions into an expression again. Because if the tokens tagged with a position and they occupy the same position, then the states that it's going to recombine are going to be multiple states.
Right.
Because it's not going to be a unique way to make an expression again.
Okay, well, let's try a different way of breaking up the states. Let's say, for example, I want to break up. What does it return here? Is it a list of?
Yeah,
list
of states, whatever the state is.
Okay, so it takes in tokens and it returns a list of states.
Yeah, it takes the list of tokens, right?
Okay, so if I were to say this thing arrow identity, then every token becomes a state. Is that right? That's not quite what I was expecting. I would have
Maybe it's
expected
list identity. You should wrap it. Also, or you should take a union also if you want. The default is list of union. List of apply union. Because the input is not just the list of tokens, it's the list of tokens, because they also separated by, depending on what event it corresponded to.
that's a very different result here. Oh, I'm confused. I mean, in this case, I thought what was going to happen is it was going to pick up every event was going to end up being a separate token, but that's not what happened here.
Yeah. So, okay, hold on. What was the recombination function again for this example? Just an identity. So the input to the recombination function, the list. So we have like an output, just a list of output tokens, depending on what of the events. So it's gonna be like a list of one, list of 0, and if you make an identity, each of those would make a state. So how many events were there? That's how many states you're gonna get. So I think it's correct. Yeah.
Well, okay. So if I were to say, for example, flatten there, that fail?
Oh, because it's because the tokens are getting renamed. Just specify a level for the flatten or catenate.
Okay.
Oh no, maybe not like that. List of catenate. You still need to make a list out of it.
Let's go only one step and see what it does. Okay, so those two, gosh, this is complicated.
Maybe change the aspect ratio. Make it wider.
Okay, what's happening here?
Just all the outputs are just getting combined into one state. So the
Okay.
state at the second step is just list of those 5 tokens.
Okay. Okay. Okay, let's zoom out for a minute and then we're going to turn to slightly different things. So the zoom out is between what Nick has got and what Ian has got, we are working towards having an evaluation graph, I think. I would like to understand the relationship between this and events, because these edges basically have events on them, I think. And Nick, if you were to prune this to a single way graph, you should be able to systematically do that. You would have something which, okay, if we did that with something which involves drill down. So the only difference in the case without drill down, the single way graph is just a path graph, correct?
Yep.
So yeah.
Okay, so with drill down, it becomes more elaborate.
Basically, if every function has a hold attribute all the way until you get to the end, you get a path graph.
Yes, because there's no drill down. Okay, so meanwhile,
sorry,
go ahead.
I think it would be useful in the diagram and on the left to have 2 colors for things that are not evaluated and things that are fully evaluated.
Mhm.
And then, for example, the first F in these vertical lines will not be evaluated. The lower F would be evaluated, and we would see that these horizontal lines with dots would always start with evaluated expressions. And that would justify why we need 2 colors and why we have to go through the change of color before applying the horizontal lines.
Wait a minute, you're saying that things that have, so
Look at the trace original goes to true example instead. This.
okay,
So, Jose, did you want to explain, or I understand? Like the top F of 3 would be a color representing that it's unevaluated, and so is
Right.
the F and the 3. But the
Exactly.
downward arrows would connect to, the F and the 3 at the bottom would be the color that represents evaluated.
Exactly.
And so would the F of 3. But the point
Okay.
is, as soon as you do a horizontal transformation rule that connects an evaluated thing to an unevaluated thing.
And so you have to go through the process of evaluating the parts again until you have an expression that is fully evaluated, and then it can, say, develop a horizontal line again.
but so yeah, that's a good thing to do, to color that. But I mean, that coloring is essentially you've reached a fixed point, if I'm not mistaken.
Mhm.
Yes.
But in this case, you thought you reached a fixed point with F of 3, but then F of 3 suddenly jumps to something else.
Well, it's not a fixed point. It's like I have evaluated all the parts, so now I can look at replacement rules applied to the whole thing.
Yeah, but there's
The fixed point for f of 3 is 3 all the way at the bottom.
yeah, I know,
Yeah.
confusingly.
Well, because it has to go through all of this stuff first.
Yes, I understand that. But what I'm saying is this f of 3, after one evaluation,
No, it has not done an evaluation yet.
Exactly.
Like-
It has evaluated its subparts.
Right.
okay, so these things here are the end of the line. They're fixed points.
Yep.
Right? They can get a different color.
Yes.
Yes. So that's
And-
why
and
we
like
need the
that
two Fs.
plus there has a different color as well.
Yep.
Okay, but so the whole point is you don't bob back up in the recursion in the tree-like recursion in the evaluator until you have built yourself on solid foundations. With our current evaluator, we don't recurse back to the top of the expression again until all the subparts are stable. Correct?
I think that the confusing thing here is that once you have evaluated the Fs and the 3s, the f of 3 appears above. And I think it would be perhaps a bit more natural if it appeared below.
Yeah, I agree. I agree. That was kind of what I was saying, except rather confusedly. That because it has to go down and then up again. So here, yeah, that's a good point, Jose. If what happens is this one is a downward facing one, and this one is a flipped around, sorry, it deconstructs itself downwards, and this one constructs itself downwards as well.
It's tree layout top versus tree layout bottom.
Yes, exactly. Is it possible to change that in this picture, or is that way too custom? Okay. And how close is this picture to actually being implementable?
I mean, it's just tricky. I think there's like you might be able to apply some like decomposition of this into rectangles techniques that Jose is familiar with for this.
Okay. But the basic point here will
But
be
I can generate this graph, at least with the edges and vertices.
okay. Now, just to understand, this is a single way evaluation where the two kinds of edges are transformation and drill down. And the colors, and there's this third one, which is the stay the same. I'm already a fixed point. I just want to be, it's just the building materials edge where you're transforming the 3 into a 3 that will be used as a piece of building material, so to speak, to build back up the f of 3.
Yep.
Okay. Do we understand, does Nick understand, for example, how this relates to his graphs? So his state nodes correspond to the finished goods, the finished constructed trees, if I'm not mistaken, or could correspond to that. And the state node is then connected through an event to a new state node. Nick, did that make any sense? I mean, do you understand this relationship or?
Well, not quite. I don't think the state is being produced every time during the tracing at all. You just every time you doing the drill down, you're not making up the state again. But
in the
state
drill down,
represents the whole expression.
Okay. No, but I mean, look. This
Is it correct
thing
that the
here-
states are the roots of these trees?
which is that one there, and then that one, which turns out to be the same.
With an option to suppress it.
So like states are like what if you make a slice for this tree there, and at each step, and to combine it at this particular step, what would be the expression at this point? That would be a state.
Is it always a single expression, or can there be multiple ones?
Well, for a simple evaluation trace, it's going to be a single expression. It is unique.
Okay. Okay. Let me see. So, okay, but then, okay, can you give me a sense of how do we go multi-way from this picture?
Well, maybe you make it wider
Yeah, but what's actually happening?
somehow.
What's happening is,
you have the evaluator, which is a lot of complicated transformation rules that applying one step of it goes from f of 3 to plus of f of 3 minus 1, f of 3 minus 2.
yeah. No, but I mean,
all the little like sub detail in this is just detail about that transformation rule, not about different ways that it could be applied.
right, as opposed to Nick's stuff over here, before we even get to the states thing. This is different evaluation paths, which are confluent in this case. What is the condition for them to be confluent? Or is it always the case that any reasonable, I think it's always the case that any reasonable functional programming type thing will always be confluent.
Yeah, I think the condition is that your rules don't overlap. So if you don't have a separate f of n that is doing like a completely different thing.
I see. So in other words, at every point, okay, so the condition for confluence is that at every point there is unique transformation that can be made. No, not a unique, every subpart. See, because this whole thing has two transformations that it can be made from here. You can either expand the f of 2 or you can expand the f of 1 here.
Yeah, well, but if there is an overlapping position, they happen a different position, but if they overlap, they should be unique. There only should be unique way of doing it.
Are there up values in which
Okay.
you can get that, in which you can get this overlap and non-confluence? I bet there are. I bet it depends on what. Yes, there clearly are. It's like, does an up value, if an up value is okay, so the claim would be non-confluence can occur with up values. And I will claim that an example of that would be h of f of x comma g of x. And the question is, who gets to grab the up, who gets to make use of an up value, the f or the g? Do you get what I'm saying?
Yeah.
I think that will be a case where there is non-confluence. I have to choose precedence for f or g. What does it actually do? What does the evaluator actually do in that case? Anybody know? I think it presumably picks the f there first. Anybody? Jose, Christopher, anybody know what the evaluator actually does?
I think you can even achieve it with down values. It's like it always picks the first rule with like the most general one case, whatever. What is the rule?
Right.
But it can pick like all of them.
Well, but normally the down values, I mean, the way that works is that when you add down values, they get put into this list and the list is sort of sorted, but up values are in a different list. So it can't just, like with down values, it's literally going down the list and picking the first one that's there.
Right,
But
but
up
this,
values
there'll be
are not
an
on the
F
list.
list and there'll be a G list for the two different up values here. So it's.
But I mean, even things like, do down values have, up values have precedence over down values, right?
Yes.
Okay, so it goes down the up value list first, but then the question is which. I'd assume it goes down the left one first.
I would assume that also, because I think that's its general principle of leftmost, innermost evaluation. Or is it innermost, leftmost? No, it's leftmost. Which one is it? Ian, do you know from your tree work?
Is it outermost, leftmost?
Right, but for down values, it's. Well,
I mean,
what
it's
does it
big.
do?
The
No,
whole
it's not
outermost,
argument.
innermost thing is kind of subjective. Like you're going to go down and then you're going to go back up either way. It's like, do you
Okay.
visit? Do you apply? Do you do some operation while you're descending the tree, or do you do it while you're ascending the tree? But
Wait,
it's
but up values are,
leftmost is like it's a depth first. It's a like in tree traversal order. It's a leftmost, or it's a left to right depth first traversal.
right, but up values are yet a different thing though, because what up values are is just that every time it reaches an expression to evaluate, it does a quick little check where it goes sort of down level, checks if there's anything to do, and then it goes back up. Right, because up values only work one level down.
Right.
And then there's
That was-
also like sub values and how do they play with all of this? I don't know the details of this.
Right.
Up values, I'd imagine, are more like down values, but yeah.
I would think so also. I think that in the end, what should happen is that there should be events that are essentially down value events, up value events, things like this, or something like that. And okay. So what this picture illustrates is that the series of intermediate expressions you can get is different depending on which. If you are traversing the tree, there are different tree traversals that will lead you where you perform the transformation on different tree elements first. And this graph represents all possible orders in which those transformations could be chosen to be made. And so the different sub-expressions, yeah, I think that's okay. So I'm trying to understand in this graph here. So this is a single way graph. My gosh, this is confusing. And then the next question would be, it would be useful, Nick, to see in this multi-way setup what a natural coding of something like an n queens problem or something would look like here. Or some trivial game type thing. Because then what we should see, in other words, if we were doing logic programming, what's the most trivial logic programming example? What we should see is that this graph in a logic programming case has many different outputs, probably does not have confluence. And what we're asking is, what's the largest value that can come out in any of those outputs, let's say, following, where we don't know the path and we don't know, and we're looking at a collection of outputs. In other words, this is attempting to turn this into something which looks like logic programming, as an example. Right? Because this case here, it's like evaluation, but you can do the evaluation in different orders, but you're always going to get the same result. It's also the case that these transformation rules can define something like logic programming. Am I right about that? Nick, Christopher, anybody else?
In some way, it's like I had this example with propagator networks, and those rules can be somehow describing each propagator. Then you fill the values. For example, you fill the resulting value that you want to achieve, and then just run the network, and all the intermediate values getting filled. Unless there is a contradiction. If there's a contradiction, then contradiction, as soon as the contradiction appears anywhere in the graph, it getting propagated along the whole network.
I don't quite. What do you mean propagation? What do you mean by that?
Well, maybe I can show an example.
Yeah. You want to share?
Just give me a second. Can I find the notebook again?
Or you can send it to me. Okay, but our big picture idea, question, whatever. First objective here, the evaluation graph, being able to show what it looks like. Next objective is, in the evaluation graph, be able to easily see what are the possible, what are the possible evaluation orders, and from the graph theoretically, figure out what things can be done in parallel. Like, let's imagine we were running this on GPUs or something, and we wanted to split the thing up into different threads, or not GPUs, let's just say multi-threaded. What attribute of this graph would show us there can be different threads? Like, for example, here, probably that block is separately from that block. Is that a true statement?
If you don't have side effects.
Well, we're dealing with let's deal with a non-side effect case, okay? And then what I want to ask is, in this evaluation graph, you should graph theoretically be able to say what things can be evaluated in parallel.
I think if you assume there aren't side effects, then you could just switch every depth first thing to be a parallel breadth first. Just trivially.
Okay.
Like instead of evaluating f of 3 minus 1 and then f of 3 minus 2, just when you do the standard evaluation sequence, just evaluate all the arguments in parallel.
Okay, that's back to the parallel attribute of SMP. Well, what happened, Christopher? You maybe we're going to think about whether there's a way to just try doing that. I mean, would our evaluator code actually allow one to do that? Just say, assume no side effects, just switch on a parallel block, and then everything here, every function just gets all its arguments updated in parallel.
I mean, I think it's, I don't know enough about the sort of, internal workings of the evaluator, but I mean, certainly there would be things like everything you do will touch the symbol table in some way, every time you do a block or every time you do a module and stuff like that. So I think it's more complicated than, just launching a bunch of threads or something, but it might still be possible.
Right. You're saying that, for example, the module number is definitely not going to be multi-threadable. It would have to be a UUID, for example.
Maybe. I mean, there's probably ways with like a mutex and things of doing the module number. But I was even just thinking about the fact that you're creating symbols, which is, changing the symbol table.
Right.
I mean, even if you just have a program that just says, right, unique or something, that's, for forgetting about module number, it's already not gonna,
Right,
yeah.
but that's not every. I mean, the question is, could we set it up so that we can detect this subpart of a program is fully parallelizable? Every function here has, or even just some functions can be multi-threaded.
So this is basically, I mean, right. I mean, in general, functions that are totally pure, you can just run them concurrently however you want. I mean, this is one of the principles behind, I mean, this is why Haskell can have a lazy evaluator.
Yeah.
But I think trying to, I mean, maybe we can, I'm thinking about if it's really realistic to be able to statically figure out if a program is pure. I'm a little.
There's got to be a lot of functions where it's easy to tell that. I mean, I don't know whether.
Yeah, but then there's things like, I mean, for example, if it uses module, it's technically not pure because it affects the module number kind of thing, right? So I mean, but you want that to be considered pure.
Yes. No, but I mean,
but you could imagine weird things. You could imagine weird cases where the fact that it affects the module number does actually cause problems. But yeah.
Well, okay, but let's imagine, thousands of functions are going to be pure, slam dunk pure, I claim. Thousands of functions, there's not going to be an issue at all.
Sure, like binarize or
yes,
reverse.
Right. I mean, there is potentially an internal issue because there's caching and things. Then I have no idea whether our caches are thread safe. Does anybody have any idea? I think we have a uniform caching infrastructure that's used with weak hashes and so on. Anybody know about that here?
I'd be shocked if they're thread safe. But in addition to caches, there's also stuff like, there's random pieces of functionality that use, hash tables and stuff. Like I'm thinking of, for example, some of the stuff that deals with like message handlers, like $message list. I think that makes like a hash table and it, updates it as it goes and stuff like that. That's something where, figuring out how message lists work with concurrency is a little bit funky.
That's funky. That's already funky with parallel evaluate.
Another one would be code that includes, well, how aborts work. Because normally, well, actually, I guess aborts, there's probably a reasonable way to do it with aborts, but like normally speaking, it's you know, if you have like a throw in one of these concurrent threads, it has to abort the other threads before
God.
it, you know, goes up, for example.
Look, these corner cases are ugly, but that doesn't mean we can't make something work for most cases.
Yeah, of course, of course. I'm just saying that, you know, you've asked several times, you know, whether this is just like kind of a, you know, an easy little thing where it's like you'll have to write a small amount of kind of tricky code that will then magically make things run concurrently. And I'm saying I'd be surprised.
Right. But my claim would be certain functions we could tag statically, lexically. We could say this piece of code, if it runs only these functions, is, you know, is going to be okay to run, you know, multi-threaded. I mean,
yeah, I mean, I would sort of guess. I mean, that's kind of the inverse of. So the thing we talked about before was having an attribute, you know, where the arguments of a function and arguments of the tagged function are run in any order, as opposed to,
yes,
you know, any expression that contains
fine.
these functions.
No, I agree that that's a fine thing to do. I mean, we could just add an attribute, just like we add listable. You know, listable is an attribute. Parallelizable would be an attribute.
I don't know that it's really parallelizable. It's just that the specific step in the evaluator of evaluating the parts of an expression can be done in parallel. It won't magically parallelize any of the algorithms that those functions use.
Right. And I think also technically that the correct term is concurrent, not parallel.
Well, fair enough.
Parallel means like it's running on different cores and stuff, but concurrent just means that like you make no statements about the order in which it's going to run.
So you're saying that the thing we have then is the concurrent, what will be the adjectival form? Concurrentable. What the heck would it be? What is the adjectival form of concurrent? Able to be concurrent. Concurrent.
Why are attributes? Well, hold all is hold all. It's not hold allable.
Yeah. Okay. Well, concurrent just seems funny, but I mean,
what's the relation with orderless?
Horrifying.
Orderless ignores the spatial relationship between the arguments, and this one ignores the time-like separation of them.
Actually, does orderless, out of curiosity, does orderless reorder and then evaluate, or does it evaluate and then reorder?
It reorders, then evaluates. And actually, the pattern matcher can look at all orders. So the claim would be orderless is spatial independence, argument concurrent, not a very good name, is temporal independence.
For parts of expressions.
Well, that's interesting. I mean, we really should try some experiments on this. Here's just a very practical software engineering question. Is it the case that there are good enough C analysis tools that even for the kernel, we could actually figure out, for the C kernel, we could start figuring out what blocks of code can run concurrently? Is that plausible?
I don't think so. I mean, I haven't really seen much stuff like that, but I think the reason I haven't is because it's like one of these things with you know, with the module number, where it's sort of like if you're being really picky, nothing is pure. And so, yeah, especially C code, it's very, very hard to know if something is really pure.
So, okay. We got weird background noise from somebody here. Okay, well, okay, so let's just understand our objectives and then should wrap up fairly soon here, but just our objectives right now. Okay. You know, one thing is, you know, can we merge the Nick and Ian evaluation graph technologies? Is that a reasonable question, guys? Everybody's silent.
Ambitious.
It's more a question, how would you make an evaluator multi-computation already?
Well, okay, but I'm happy. Okay, so first sub-step is what is the single way version of Nick's, graphs? And here,
How do
okay,
you
so
but also how do you represent other evaluators?
what do you mean by other evaluators?
Because the trace graph is so deeply like it is the standard evaluation sequence.
Yeah, but as you were about to say, it really doesn't have a huge dependence on that, does it? I mean, in other words, you could rewrite it.
Well, I'm saying the horizontal edges are the application of down values, up values, or sub values or own values, not arbitrary rules that could be applied at arbitrary sub expressions of the expression.
Okay, but let's start. Okay, fine.
Specific transformations.
But let's start with that. Let's start with the star value transformations in our language and see if we can understand what the analog of Nick's got. See, what I think is going to happen is Nick's events will come in a down and up, a sub, and an own variety or something. That's my claim. And maybe an internal code variety. What's that?
That's possible, yeah.
And then, so then the idea would be, okay, let's understand what the point of an evaluation graph will be. One is to be able to do graph theoretical operations on it to understand features of the code. That's one objective. Another objective is, well, I mean, okay, a long-term objective, like a 35-year objective, has been, can you understand a loop, for example, and can you see it in the evaluation graph and just be able to kind of like a puzzle piece, take a loop and put it somewhere else, for example, or see how to make a loop by just extruding identical pieces of the evaluation graph. In other words, spatialize, well, I don't know what space this is, but graphify what would otherwise be a program counter. In other words, can you get rid of the program counter and instead represent it in terms of kind of the dependency structure of this evaluation graph? Did that make any sense?
I'm not sure. Are you wanting to like step through this graph?
No, I'm saying, imagine we have a piece of code that is written as a loop. Then let's look at the evaluation graph that we get from the piece of code that was written as a loop. That graph will have many identical elements in it. Okay. Now we say, instead of programming by writing a loop, we program by having a way of putting down puzzle pieces that correspond to the evaluation graph. So it's like visual programming. Okay, it's a generalization of visual programming. Did that make any sense? We can imagine this graph.
For example, like if you did a table, you would see the expression in the table reappearing many times in this graph.
Yes, but even if you had a for loop that had a, what you would see is that for loop would have a copy in the graph of boom, 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 boom. And then what we could say is, instead of specifying it as a loop, sort of from the outside, a function that just does the looping. Yeah, I mean, here's the point. Table has internal code that produces the separate elements in the loop. What I'm saying is, could we have a way where you say, okay, I want those separate elements in the loop. I will make that by just having this visual collection of puzzle pieces that I set down to represent that loop. Make sense?
Nick, this makes sense, right?
Maybe.
The thing is, I think at least this representation, if you looked at a table or a do or whatever, it would be very verbose.
Sure. That's okay. I mean, that's okay.
And the visual
What's the
size of
problem
it
with
will
that?
correspond to how many times it runs.
What?
So if there's 100 iterations, it's going to be 100 times larger of a graph.
Yeah, great. That's what we want. We're trying to understand, okay, the real point, this is a sub point about evaluation graphs. You know, when they're a program count, one of the things that's horrifying in procedural languages is the hidden state of random values of variables, random program counters, things like that. Okay, but in our evaluator, there is a little bit of hidden state. You know, certainly when we have down code, there's hidden state. But the idea is to expose all hidden state and make it explicit in the actual structure of the evaluation graph. So I'm saying, so instead of saying there is a loop, it goes around a certain number of times with a hidden internal variable, internal code, you just say, here's a graph that represents the evaluation I want to take place. And then in a sense, I mean, Nick, it reminds me a little bit of the MetaMath system's proof mechanism, in the sense that in the end, when you want to do the proof, it's just like ripple through the code. You have nothing to do. It's a trivial evaluation. Whereas a loop right now, you know, a loop requires that there's internal code that's messing with program counters and things. Whereas what I'm saying is
we're just unrolling the loop to make it completely explicit visually, graphically,
Yes.
even though it's highly redundant. That's better than having some implicit hidden part.
that's the idea, because then there's a meta programming, a sort of meta level at which you can say, now I will be constructing the graph. But you can say it is just puzzle pieces in a graph.
Yeah,
it's
right.
not,
Yeah.
there's no, and by the way, when you get to do that, there are potentially all sorts of interesting generalizations you can make and so on, because it is now a graph theoretic construction rather than a hidden state type, you know, hidden state as in program counters and things type construction.
It's also related to the unfolding the recurrent network layers.
Indeed it is. Indeed it is. Which is, you know, people have done exactly this in neural nets of this and I mean, in that case, the reason they're doing it, and this will again relate to what we're trying to do, is, you know, they're doing that partly so that you have trainable pieces, so that you have something where, you know, because if you have a program counter type thing, there's no weight that you can identify. I guess that's why they're doing it. Why are they doing it? That's the reason, right? I mean, it's to be able to do automatic differentiation and so on. Yes. Anybody know? Wrong group here.
Well, maybe they're doing it to optimize something, how to actually put those layers on the GPU and so on.
That's possible also. Okay, well, anyway, so I mean, we've got the sub-project of argument concurrency, which is a different thing that is kind of somewhat independent of the things we're talking about here. We've got this effort to basically make the evaluation graph for our evaluator, essentially. The evaluation graph, first of all, single way, and then to understand, yeah, this is, I would say, the path. We make the single way evaluation graph for our evaluator. Then we imagine what it would look like if we added an argument concurrent attribute, which I believe is equivalent. I think that's equivalent to the multi-wayness of this whole thing. Is that right?
I think the multi-wayness is like I apply an up value instead of applying a down value.
Really? Well, okay, this has to be proved. But then what we expect is, first we have the evaluation graph. It's going to look like this with different colors and different whatevers. Okay, then we go multi-way. And that gives us another dimension here, that is the branchial dimension of different possible evaluation orders.
It's like every horizontal line or every horizontal edge here, there would be many horizontal edges. corresponding to different rules.
That's correct.
Or applying them at different parts of the expression.
I think so.
Whereas our standard evaluation is like this certain thing in terms of down values, up values, etc.
Yeah, exactly. But then the question would be, okay, then what are we trying to achieve from multi-computation? What we're trying to achieve is that, you know, our normal programs, okay, normally you run the program, you expect to get to a fixed point from the single path of evaluation. We then have new meta evaluators, so to speak, like the evaluator that says, just find me a path that gets to a fixed point. Even though I know there are 10 fixed points, just find me a path. It may not be, find me a path that gets me to the smallest fixed point or the fastest fixed point, you know, the fixed point that's fastest to get to, which may or may not be the fixed point that you would get to with a standard evaluator. Just like for Fibonacci, there are faster ways to do it than to do this depth first.
Yeah, I would think the graph for such a thing would be much more horizontal than this graph. If that
For
makes
which
sense.
such thing?
For like a beam search, like you're trying to find a best path.
Yes.
It's like lots of transformation just from one state directly to another.
Possibly. But I mean, right. But I mean,
Instead of doing depth first traversals.
Right. But you see, what I think we want, you know, it's an interesting question whether the kinds of functions we're going to want are basically ones that involve rules, transformation rules, plus our built-in functions, or whether we're going to want to see the full evaluation graph for essentially our both built-in and user-added functions. I think both things might be useful. I think for these things that are more like logic programming, it might be more useful to be able to explicitly give the transformation rules rather than to have them be assignments effectively. That makes sense to anybody? So just like Nick has in his current, in this token event graph with multi-replace, be giving the rules and then asking the questions in this, you know, you could get the token event graph, that would be, or some multi-way graph, or you can have the meta evaluation operator that says, okay, so one meta evaluator is replace repeated. Okay, so these are kind of, you know, given a set of transformations, what are the meta evaluators you could use? Okay, so one of them would be just replace repeated of x per comma rules. That is our traditional fixed point. Yes, makes sense to people. Another possibility would be saying find optimal result, let's say, where we have an x per rules and a criterion. And in that case, it means, so this is just get to a fixed point with the standard evaluation sequence.
Isn't getting to a fixed point itself just an assumption that you're making about the evaluator? Like replace could be an evaluator. It's just a one-step evaluator.
Yes, that's true. Yes, that's right. I mean, so in principle, we could have replace repeated, and then we could say x per rules traversal order goes to whatever, and we might have a different set of results. Right, that would be another kind of operation. I don't know how to parameterize that traversal order, but that would be the idea. So that's different from find optimal result, which says try all possible paths that lead to fixed points and return the one that maximizes the criterion, let's say. And, you know, then there's obviously a path version of that where you also could return the path, you know, and this is exactly like find replace path. This, well, no, I'm sorry. That there's another case, which is the find replace path case. Right? In that case, we are specifying the endpoints. We say expo1, this is the wrong way around, but rules expo1, expo2. Right? Now it's find a path between those two expressions. And we've now got pretty nice technology for that. And I would say that that's, and then, then we have the theorem proving version of that, where we've got intermediate lemmas and so on, and we've got now some better technology for doing that. Okay, this case here, try all possible paths that lead to fixed points, leave the one that maximizes the criterion. And then the other cases are things like, probabilistic programming case, where you take a slice across all the paths. That's another case. Or there are probably cases which we don't understand very well yet that involve sampling and infinite evaluation. Making sense? Is this making sense to people?
Is that like lazy evaluation?
Maybe.
Like
I'm thinking about
the
an
ability
actual
to have a
evaluation.
replace repeated that never reaches a fixed point, but being able to go out like as far into it as you want.
That would be one thing, but there might be other questions you can ask about an infinite evaluation. I mean, there's plenty of the cases. I mean, I don't know, e.g., a non-terminating combinator expression, non-terminating Turing machine, combinator, etc. And I don't know what you're going to ask about it, but yes, I agree. It's like lazy evaluation. One thing you can do is lazy evaluation. I don't think that's the only thing you can do. I think you can make potentially, and this was something, you can make potentially infinite statements about these things. Richard was talking about using transfinite numbers to represent the kinds of objects that you get by doing these infinite non-terminating things. Okay, so you can actually reason about the non-terminating object rather than simply saying, show me it unrolled for such and such a number of steps. Okay, well, we probably are running out of time here, but did we have another? Oh, wait a minute. Nick had just sent through this thing about propagator networks, which we didn't look at. Find out what a propagator network is. What the heck is this?
So this is in connection with graphs and logical programming, I guess. It's like those red vertices are propagators. Other vertices are values. And then it's like you said, you put a puzzle piece, you populate some value, and then it propagates and fill all the values across the whole network.
So this is like constraint programming, like people imagine one could do with spreadsheets and things. Is that right?
Maybe.
That was one of the early claims of the wonders of spreadsheets, was that you could fill in some numbers and then you could sort of back calculate other ones. Yeah, we've never had a capability to do things like this, really. Although you could state this in terms of equations, presumably.
Yeah, like in this examples, I tried to make it more interesting by automatically add propagators, inverse propagators. You just specify one, how you go from one value to another, and all the inverses are added automatically into the graph.
See, what's interesting here, and we have the wrong people to really discuss this, maybe Tony has opinions about this, is that we can imagine this is in the category of evaluable graphs. Graphs that have, I mean, like Ian has one version of that in what is it?
Treefold.
Treefold, yeah, right. Treefold. That's one version of an evaluable graph, where you put an operator on each node and then you run it. So this, in a sense, is some other version of an evaluable graph, I claim.
Yeah.
That make any
Like a
sense?
simple example, like find an example with temperature. It's somewhere in the middle. I think temperature converter. The most obvious one. So I can just specify two propagators how you convert from Fahrenheit to Celsius and from Celsius to Kelvin. Then just two, and those inverses are added. And then you can just fill any out of those three and you get all the other two values. And you can do it by interval. It's like, yeah.
Right.
And Nick suggested that one application of this to the tags is that we could also get events that basically know their inverses, so that you could basically take a tag, and if you need to reverse it, that it can become reversible.
How does that relate to quantum computing? I mean, those gates, the tag is going to be super similar to a quantum circuit, I would think, in that situation, where the gates are the events. Am I wrong?
Oh, if you would think about all those states and operators and gates as just tensors floating around, then it's not really different from even usual neural networks.
Yeah. So, well, where the neural net is, where this event is then one of our layer operators, basically.
Right.
Right? It has certain things that come in, and then it's a layer operator, and it goes out. Oh, very interesting. What a grand unification we're heading for. Okay, so I mean, these are interesting. These networks. I mean, I think it's a pity Roger isn't here, but I mean, or actually, Michael Trott has also thought about these, because our formula data system works basically like this. We should talk about that, exposing that, because it should be the case. Okay, so let's say in the propagator network here, I claim that formula data, well, actually, I wonder what, let's say, what the heck is this? Let's look at Snell's law. I don't even know what formula lookup is. Maybe it shouldn't be. Okay, so formula data. Oh, that's really stupid with the double quote there. Okay, but I believe that formula data has this feature that it has all the inversions. So you can fill in any set of parameters, and it will fill in all the other ones. Does that make sense? So I think it's working in the same kind of way. All right. Okay, was there anything else we were supposed to be covering? Oh yeah, this is cool. Does this work, Nick?
The Sudoku one?
Yeah.
No. I think I never managed to make it work.
But you think it should work?
Yeah, I think it should work. It's just in this particular implementation, I don't know.
Okay, but then what this is, okay, so this propagator networks thing is a version of a meta evaluator, if I'm not mistaken. There is a set of rules defined. I see that is okay. So that then when there are two-way rules, and most of what we're talking about here is one-way rules, but it's like when there are two-way rules, then you can get propagator networks, presumably. Then you can and other things like that, which is different from these things here, which are essentially one-way stories, if I'm not mistaken. Okay. Other things we should cover here, last minute or two?
There was supplied, but I don't know if we have time for that.
Well, that's a whole giant, okay, so that's a whole giant discussion. I think we should have broken that out into a separate meeting, really, because I think that's I mean, what's that? I think it's an ILD story. I mean, this is transitioned from sort of a special project point to an ILD point, if I'm not mistaken. I mean, I still don't like the name. Wow, that's an interesting one. The most recent intermediate results of previous applications of F. Wow.
Yeah, the test in nest while is implicitly like a supplied together with the next argument.
Yeah, that would be cool. Don't you think, to be able to have the sort of trace back of what did you last see in the map? Wherever you were in the map, wherever you were in the traversal order, what did you last see? If it can
It's
be
maybe a little
implemented.
bit also like moving or block map.
Yes. Yes, except as a block map with weird multi-level stuff.
Yeah, these are like the simple cases: map thread, subset map, block map. I feel like those are going to be very specialized.
Right. Well, we'll have to find a way to document these things, probably in there, just like we do for things like, color function and so on. We'll have to put it in the actual thing that uses them. I wish we had a better name than supplied. I really don't like supplied. We had a variety of names we were thinking about, right? We had the name.
Yeah, there's like a whole notebook that lists candidate names.
Where was that list?
Hold on.
This folder is becoming a mess and we should clean it up. This multi-computation folder. I
think it's oh. Well, there were a number in SW notes 8, but maybe not for supplied. It's for using.
Oh, that's the
ambient.
same thing as supplied. Using is supplied.
So supplied is the best name, in my opinion, so far.
Is supplied even on this list? It's confusing because it's not even stated here.
No, so
It should be added.
this was from a meeting before
Oh,
suggested supplied.
Supplying. Giving. I'm going to add this in here, even though it's counter. Okay, so supplied. Whoops. Supplied, supplying would be okay, except it's too long. Giving. And the problem is that the most common case. What is the most common case? The most common case is a one argument form, which doesn't say what it's supplying, correct? Am I correct or am I not correct?
No, I'm
I don't know what you
expecting
mean by
that.
most common.
No, the most common case is going to be something like, hash expression hash index, something like this. Right? That's the most common case. The case where you explicitly name the things you want. This is the case where it's going to lexically scan to find out what it should be picking up. Right?
That is the lexically scanned case, yes.
Yes, but that's going to be the most common case. That's what people might write most of the time. The case where you explicitly say what to pick up, Why would you do that? If you know the names of what to pick up, why would you not include them lexically here?
Like if you're writing code, like a package,
Yeah.
you're going to want to use functions with
Why? Why? Oh, you mean sub functions here?
I am never going, me personally, I'm never going to want to use this with a pure function because I'm implementing things in packages. I am going to want to use supplied of LMs, comma.
I guarantee you will use this all the time in code where this is just doing it right there.
Maybe if I personally did more like interactive coding, that would be
no.
good.
You'll end up using it for real code because it's going to be a small sub piece that does it right there, not something which digs into the functions here. In any case, it doesn't matter. I mean, because you might just say f of hash index, right? You're
then you're giving up on things like attributes.
Some people don't use pure functions very much. I'm guessing that's what you're talking about. I mean, like you just define a function separately and then map with that, as opposed to defining a pure function in line.
all right, fine.
I mean, you will have to add boilerplate just to use standard function definitions in the language with this. You'll have to write function with like 3 arguments if you want hold attributes or whatever.
I know, but that's an unbelievably corner case. I mean, this will be the most common thing is people generalizing map index, basically. But it doesn't really matter. The name has got to work in the 1 argument case. We're not doing a name that is primarily for the 2 argument case. It's got to work for the 1 argument case.
Yes.
So
I think either way you write it, it'll like will naturally read well, because if you have the 1 argument case, you're going to see the named slots, and if you have the 2 argument case, you're not.
yeah, I get it.
So either
You got to go.
as long as the name works for the 1 argument case, I think it'll work for both.
Okay. What about giving?
Like giving the arguments.
Well, giving index and expression and whatever. Supplied just is not sitting well with me. It's not.
I don't like supplied either. I'm not sure about giving though.
Giving is weird as well. All right, we've got more thinking to do on this.
They're both somewhat ambiguous. I mean, I know that sometimes these. Is there any way that we can add some specificity without making the name too long?
No, it's got to be really short.
Yeah, but you can find a short word. Like
I know.
Yeah.
So it'll be a short, essentially branded name, just like manipulate, dynamic, whatever. All these things.
Right.
The name becomes the brand of what it's doing. Okay. Anyway, for another time. All right. Good stuff. Thanks, everyone. And actually, let me just check one thing here. Right.